Today, let's look at Unit 3. This would be lesson number 5, the real zeros of a polynomial function. This would be chapter 5, section 6. So to do this section here, we're going to work with some higher degree polynomials. So we're going to touch on some division strategies. So if a polynomial is divided by another polynomial, if the remainder is 0, then the divisor is also called a factor. So a simple polynomial would be, say, like, 10 divided by 2. 10 divided by 2 would equal 5. So the 2, since it's the divisor, is going to equal, it's also going to be called a factor because it went into it evenly without a remainder. Now, for us, it's easier to see remainder math if I do like 2 into 10 using long division. So remember, the 2 here is called the divisor. This 10 is also referred to as the dividend. And the answer up here is referred to as the quotient. So if 2 goes into 10, in other words, 2 times what is 10? That'd be 5. 5 times 2 is 10. When I subtract, notice how my remainder is actually a 0. So that 2 is also called a factor in this situation. So is the 5 for that matter, since you can reverse it. So remember, that's how we found factor pairs using big T, was just that. Finding factors was using division. Something else to bring to your attention in long division, we can actually do long division in a strange way. I could say 5 goes into, instead of saying 5 goes into 128, I could change 128 to a polynomial by writing it as 100 plus, 28 plus, let's change that to a 20 plus 8. So I'm using the word polynomial. Remember, a polynomial actually has to have 2 more terms. So technically 10 divided by 2 equals 5. It's not really a polynomial just yet. So 2 or more terms, basically. So 100 plus 20 plus 8. So notice how we could go 5 into 100 by just saying, ignoring the 0, and say 5 goes into 10 2 times. So 5 go 120 times. But 20 times 5 would be 100. And when we subtract, we would get a remainder of 0. So then I would bring down the 20. 5 goes to 20. In other words, 5 times what is 20? We would see that would be a 4. 4 times 5 is 20. And again, we would get a remainder of 0. But when I bring that 8 down, 5 would go into 8. 5 times 8. 5 times what? 5 times what gets me something close to 8 would be actually just a 1. 1 times 5 is only 5. This time, notice how I get this leftover of a 3, remainder of 3. So if I put this all together, notice how these are like terms. 20 plus 4 plus 1 would be 25. So I'd have 25 with a remainder of 3. We also can write this as purely a quotient. You can say 25 plus 3/5, and that would be the actual quotient. Or we actually refer to that as 25 and 3/5 using the shortcut language. So 25 and 3/5 means 25 plus 3/5. So applying some of this to dividing polynomials, it kind of does the same thing, but just the math does look a little bit different. So let's divide this 4x cubed minus 3x. Let's call this minus 3x squared plus x plus 1. So I'm going to have x plus 2 on the outside. That's my divisor. And I'm going to divide that into our polynomial, 4x cubed minus 3x squared plus x plus 1. So x is going to go into 4x cubed. In other words, x times what matches that? Well, I need a 4 and I need an x squared. So x times 4x squared does make that perfect. So that's nice. So then I multiply the 4x squared times my divisor, and I'll put that underneath. So 4x squared times x would be 4x cubed. 4x squared times 2 would be a positive 8x squared. Okay, so we have to subtract, but in algebra, since we're dealing with variables, a lot of times what we'll do is we'll just change the signs and add. So 4x cubed plus negative 4x cubed, that's just going to zero out. Negative 3x squared and negative 8x squared would be then a negative 11x squared. I'm going to go ahead and bring down the plus x and go ahead and bring down the plus 1 so I don't lose those. So then our attention turns to this x and figure out how many x's does it take to get this negative 11x squared. In other words, x times what will match that. So the missing piece would be I need the negative 11 and an x. A negative 11x times x does give me this negative 11x squared. So I'm going to go ahead and multiply this negative 11x to my divisor. That's going to be negative 11x squared. And negative 11x times 2 would be negative 22x. But instead of subtracting, what we do is we change the signs and add. So the negative 11x squared and the 11x squared zero out. I have 23x plus 1. So the 1 slides down. And then x times what gets me this 23x. Looks like I just need a positive 23. 23 times my divisor, 23 times x is 23x. 23 times 2 would be 46. So again, when I subtract, I want to change the signs and actually add. So negative 23x, I'm sorry, 23x and negative 23x will zero out. A 1 and a negative 46 would be a negative 45. So at this point, this would be our remainder. So x plus 2 would not be a factor of this polynomial because I got a remainder. So I could still write my quotient though with a minus 45 over this x plus 2 as my answer. So let's ignore the one I've got on your paper and let's look at one not quite, well, kind of got some crazier numbers too, but let's look at this one instead. This is kind of more from your homework. So the divisor again is going to be this x squared minus this 13x plus this 1. And I'm going into x to the 4th. Now, when I write my polynomial inside here, it's a good idea to make the coefficients go down. X to the 4th, since there's not an x to the 3rd term, I can use a placeholder of 0x to the 3rd because 0 makes it go away. So it's not really there, but it holds a place. We do have a minus 167x squared. We do not have our x term. Our linear term is missing, so I'm going to again use a little placeholder of 0x. And our constant is this plus 1. So it goes on out there a little bit further this time. So again, we kind of do the same thing. X squared times what gives me x to the 4th. And we do see that an x squared would work there. And then we're going to multiply this x squared to our divisor. So it's going to be x to the 4th minus 13x to the 3rd plus x squared. So make sure you line up your terms correctly. That looks okay. So again, when I subtract though, I'm actually going to change the signs and add. So the x to the 4th and the negative x to the 4th will cancel out. We have this 13x to the 3rd comes down. And then we have a negative 168x squared. That's a freaky number. We'll go ahead and just bring down this plus 0x and this plus 1 before I forget about them. They get too far up there and may forget to bring them down. So now we're going to try to figure out, well, x squared times what gives me this 13x cubed? Well, I need a 13 and another x. So a positive 13x would work. So 13x times x squared does give me this 13x cubed. 13 times negative 13 would be negative 169x squared. And then I would have 13 times x would be 13x. And that would be it. So again, we have to subtract, but what I do is change the signs and add. I think you see that pretty much in everybody's videos that they do the same thing there. Must be taught from the same cloth. So 13x cubed and the negative 13x cubed zero out. This is going to give me a little bit friendlier number. That's just going to be an x squared. The negative 13x slides down and a plus 1 slides down. So now we figure out, well, x squared times what gives me x squared? Well, I just need 1 there. 1 times x squared would give me x squared. So now I write down my divisor, or I multiply my 1 times my divisor. 1 times x squared is x squared. 1 times negative 13x is negative 13x. And 1 times 1 is 1. And remember, we have to subtract, so these signs all have to change. And this cancels out, that cancels out, that cancels out, which means our remainder is a 0. So actually, you know, x squared minus 13x plus 1 would actually be a factor of x to the 4th minus 167x squared plus 1. Okay. So that's what we do as long division. Notice how it's long. It takes up a lot of paper. Something else they created is this what's called synthetic division, or what we call artificial division, if you will. But synthetic division, we're going to look at is in the form of x minus r. So when the divisor is x minus r. So if I have x cubed minus 7x squared plus 5x plus 10, if we're dividing by x minus 12, notice that my r is actually a 2. So remember, it's always going to be backwards since x minus r is up here. So remember, we have that from, you know, x minus r is a factor. You know, 2 would actually be called a 0. So, or an x-intercept, if you will. So if I'm using long division, or I'm sorry, synthetic division, what we do is this 2 comes on this outside here. So I make a little shape, little kind of a little section off box there. Usually it's drawn like that. We put this little 2 here. And then we run the polynomial across here. But the thing is, we only write the coefficients down. And they have to go from highest degree to lowest degree. So 3, 2, 1, 0. So all the terms are there. If there's a term missing, we have to put 0 as a placeholder. So we have a 1, we have a -7, we have a 5, and we have a 10. So we write down the coefficients and the constant. Now we leave a little bit of space and we draw this little line underneath here, but leave a little space underneath there. So the way synthetic division works is we just bring down the 1 to start with. And then we multiply 2 times 1, which is 2, and we put that 2 underneath the -7. And then we add the -7 to the 2, and we get this -5. 2 times -5 would be then -10. We put that underneath the 5, and then we add the 5 and the -10, and that would give us a -5. And 2 times -5 would be -10. In this last little box, we kind of section off because this is what is actually called the remainder. This is going to be the 0. So this actually represents the remainder. And this over here is going to represent the quotient, the answer. So what happens is the degree, since it was an x cubed, when we write our quotient, it's going to be 1 degree less. So our answer is going to be then x squared minus 5x minus 5 becomes our answer. So if we start out with a 3rd degree, our quotient is going to be 1 degree less. So it's going to be x squared minus 5x minus 5. That would be our answer. So that's how we actually use what's called synthetic division, which doesn't take up as much room. But this only works really well with when it's in the form of x minus r. So if we want to divide -4x cubed plus 2x squared minus x plus 1, if we want to divide that by x plus 2, notice how, again, we're using this form x minus r. So r is actually a -2. So when I use synthetic division, we actually got to change the sign to a -2. Now, what goes inside here are the coefficients. So remember, the terms have to count down 3, 2, 1, 0. So there's no missing terms. So we don't have to put a 0 as a placeholder. So I have a -4 as a coefficient, a 2 is a coefficient, a -1 is a coefficient, and a 1 is a coefficient. When I draw my line here, I need to make a little bit of space. And how synthetic division works is we just bring down the first term, the -4, and then we multiply -2 times -4. That gives us an 8. 2 plus 8 is then 10. And then we multiply -2 times 10, and that's going to be -20. -1 plus -20 is going to be -21. And -2 times -21 is going to be a positive 42. So my remainder would be 43. So as far as the answer goes, my quotient would be -4x squared plus 10x minus 21. It would have a remainder of 43. Sometimes they write that as part of the quotient plus then 43 over my divisor, which was x plus 2. So they may write it that way as well, or just a remainder of 43. Just depends. So if I want to do this problem here, x to the fifth minus 4x to the third plus x divided by x plus 3. Again, we're using this form x minus r. So if we see a plus 3, r is actually going to be a negative 3. So when I use synthetic division, we use negative 3 here. Notice how we have a 5, but we're missing the 4. So I have a 1, that's the coefficient there. But since the degree 4 term is missing, I need a 0. I now have a negative 4. But also that the degree 2 term is missing, so I need a 0. There's then the coefficient of the x is a 1. And the constant's also missing, so I need another 0. So you got to go 5, 4, 3, 2, 1, 0. That now counts down correctly. So some terms are missing, so we have to use zeros as placeholders. So to do synthetic division, we bring the 1 down. Negative 3 times 1 is negative 3. And then we add 0 plus negative 3 is negative 3. We multiply. Negative 3 times negative 3 is 9. We add. Negative 4 plus 9 is 5. Negative 3 times 5 is negative 15. 0 plus negative 15 is negative 15. Negative 3 times negative 15 would be 45. 1 plus 45 would be 46. And negative 3 times 46, I will probably need to get my calculator, but since it's unavailable, I'm just going to have to go longhand. 46 times 3, 18, carry 1, 12, 13, 138. So a positive times a negative would be then a negative 138. So my remainder is going to be a negative 138. So if I didn't do anything wrong there, that should be the answer. So notice how it started out as x to the 5. So when I write this down, I start out with x to the 4th. So 1x to the 4th or x to the 4th minus 3x cubed plus 5x minus 5x squared, I should say, minus 15x plus 46. So it has a remainder of negative 138, or I could say minus 138 over x plus 3 would be my quotient. So it just depends on how they want that written. Sometimes they'll just leave it as a remainder of negative 138. Okay. Now, that's synthetic division and long division. Now let's get into some algebraic stuff here as well. There's what's called a remainder theorem. If the polynomial is in the form of f of x is divided by x minus r, the remainder can be determined by evaluating f of r. So if I have this function f of x equals x cubed minus 4x squared minus 5, if I divide it by x minus 3, if all I wanted was the remainder, all I have to do is evaluate f of 3, and that actually will find the remainder. So if I don't actually need the quotient, if I just want the remainder, just evaluate f of 3, and that'll tell us what the remainder is. So if I put a 3 in, I'm going to get this 3 cubed minus this 4 times 3 squared minus this 5. So we could put that in the calculator, or we could do it by hand. I'm going to let the calculator do this one just to show you what that looks like in a calculator. Some of you are still not sure where all those things are on the calculator. So again, to quit, I hit second mode to quit. So again, where did my problem go? Went the other way, didn't it? There it is, right there. So 3 cubed. So again, I can put this in parentheses, 3, close parentheses. To do cubed, I usually use the little rooftop guy right above the division symbol. Put a little 3 there. But when I do that, I still got to use my directional pad to get back down. Minus then 4 in parentheses, 3, close parentheses. I need a square there. I usually use the x squared that's just diagonal of the 7. And then minus 5. Always pay attention to where your cursor is. That looks okay. So I end up with a negative 14 as an answer there. So f of 3 would be negative 14. What's interesting, if the remainder is 0, then x minus 3 would have been a factor. But since the remainder is negative 14, that tells me that x minus 3 is not a factor. So if I have 2x cubed minus x squared plus 2x minus 3, if it's divided by x plus 4, if I want to just find the remainder, I don't have to actually use synthetic division or long division to find the remainder. I can just evaluate what r is. So remember x minus r. So r is actually a -4 here. So if I want to just find the remainder, all I got to do is evaluate f of -4, and that'll actually just give me the remainder. So it's going to be 2 times -4 to the third power minus, in parentheses, a -4 squared. Parentheses are important there for sure. Plus 2 times a -4 minus 3. Now notice how this could be hard to type into the calculator. So all those parentheses and stuff can get confusing. So another way we can do this problem is we actually can use the y equals button and create a function. So if I clear this off, I can actually put the function 2x cubed minus x squared plus 2x minus 3 into the calculator. So 2, hit the x, hit the upper arrow, cubed, minus x squared plus 2x minus 3. Now, if I want to let the calculator evaluate f of -3, or I'm sorry, f of -4, what I can do is go to the table set, and my independent variable, if it's on auto, I have to highlight it to make it turn into ask. So you have to make sure it's highlighting the ask. Mine is already. So if I go to my table, hit second, and table's right above graph, I can clear these off here somehow. See if delete will do it. Yeah, hit delete, delete. That takes those off there. So if I put a -4 into this function, hit enter, it'll give me my remainder of a -155 without having to do all that substituting in and doing that by hand. So we end up within this -155 as a remainder. So again, that would tell me that f of negative or x plus 4 is not a factor since I got a remainder. So that's some things we have to be picking up on is what does that mean? So if you divide x plus 4 and get a remainder of -155, that just means that x plus 4 does not divide evenly into that polynomial. So as I said, there's that calculator tip. You can change the table set from independent of the independent variable from auto to ask, and this allows you to pick your own x values. Okay, so we just kind of discussed that. So the other thing we have what's going on is what's called the factor theorem. If I'm given the polynomial f of x, if it's divided by x minus r is a factor of f of x if f of r is equal to 0. So in other words, if I evaluate f of r and my remainder is a 0, that means that x minus r is actually a factor. So is x plus 2 or x minus 1 a factor of f of x equals 2x squared, 2x cubed minus x squared plus 2x minus 3? Well, what I can do is evaluate f of -2. If I get 0, then it's a factor. If it's not, if the remainder is something other than 0, then it is not a factor. So I have 2 times -2 cubed minus a -2 squared plus 2 times -2 minus 3. Notice how that's a handful of the type. You could just put the function 2x cubed minus x squared plus 2x minus 3 into the calculator. I can't remember if I've already done that or not. I can't remember which one I just put in. So yeah, I've already put that in, 2x cubed minus x squared plus 2x minus 3. So if I want to determine if x plus 2 is a factor, all I have to do is evaluate f of -2. So my table, can I come up here and delete that off and put a -2 in? And that gives me a -27. So since I got -27, x plus 2 is not a factor. If I evaluate f of 1, notice how that's x minus 1, so f of 1 is what I'm looking at. So instead of putting that all in, if I just let the calculator put 1 in, hit enter, notice how f of 1 actually equals 0. So that means that x minus 1 is a factor. So without having to do synthetic division or long division, I can determine if something is a factor by just evaluating the function at specific R values, if you will. So let's move into this next part, number of real zeros. A polynomial function cannot have more real zeros than its degree. So notice that the degree of this polynomial is 7. So one of the rules that we pick up on is if I'm looking for the actual zeros, there cannot be more than 7 real zeros. So some things to pick up on here is if I was trying to find the zeros of this function, I would be looking for no more than 7 real zeros. Now keep in mind, when finding zeros, we also have this thing called multiplicities and things. So the Descartes rule of signs is something we want to look at. So the number of positive real zeros of the function either equals the number of sign changes in the terms of f of x, or it equals that number less an even integer. Less an even integer. So keep that in mind with the Descartes rule of signs. Also, the number of negative real zeros of f either equals the number of sign changes in the terms of f of negative x, or that equals the number less an integer, an even integer, that is. Okay. So if I have this function 3x to the 7th minus 4x squared plus 3x cubed plus 2x squared minus x minus 3, if I have this function here, if I want to find possible positive real zeros, what you do is you just count the sign changes of the function. Notice how it's positive right now, and now it's negative. That's one sign change. So there's a change. Now it's negative. It turned back to a positive. That's a change. It's positive. It's still a positive. That's no change. But now it's a negative. That's a change. And it stayed negative. That's no change. So there's 3 sign changes. It went positive to negative. That's a change. Negative to positive is a change. Positive positive is not. Positive negative is. Negative negative is not. So 3 sign changes. So the number of positive real zeros could be either 3 or 1, because you have to decrease by an even number of integers. So you'd be looking for 3 positive or 1 positive in that. Now, the possible negative real zeros, what we do is substitute negative x in to our function. So wherever there was an x, I'm now replacing that x with a negative x. So x to the 7th now turns into a negative x to the 7th. X to the 4th turns into a negative x to the 4th power. Just see my 4 there, aren't I? So I should have a 4 there. The x to the 3rd turns into a negative x to the 3rd. The x squared turns into negative x squared. The x turns into a negative x. And we have this negative 3. So if I clean this up, remember a negative raised to an odd power remains negative. So this is going to turn into negative 3x to the 7th. If you have a negative x to the 4th power, that stays positive. So there's no sign change there. That stays as 4x to the 4th. So notice I have a negative x to the 3rd. Since that's a negative raised to an odd power, that means that's a negative, which means there's a sign change there to a negative 3x cubed. Negative raised to a power 2, there's no sign change there. That stays as a plus 2x squared. A negative and a negative make a positive x, and this minus 3 comes down. So now if we look at this, it's negative, it stays negative, it stays negative, it turns positive, there's a change. Okay, let me do that in a different color there. So, as I said, negative, 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 positive, there's a change. Positive, no change. Back to negative, that's a change. So possible negative real zeros would be 2 or none at all. If you decrease by 2, you'd have 2 or 0 negative real zeros. So the Descartes rule of signs can help you identify whether you're looking for 3 positive real zeros or 2 or 0 negative real zeros. So that's what's called the Descartes rule of signs. So now we have what's called now the rational roots theorem. So let f be a polynomial function in the form of, we've seen that before. So the big thing is the leading coefficient and the constant's really what we're paying attention to. So in the polynomial function, we're saying each one of these coefficients is going to be an integer. So if P over Q in lowest terms is a rational zero of f, then what that means is P is a factor of a sub 0 and Q is a factor of a sub n. So what this is getting at here in this rational root theorem is the leading coefficients and the constants are going to be very key to helping us understand what the rational roots are. So what we pick up on is this P is coming from the constant. This Q is coming from the leading coefficient. So let me see here. So what we're going to get at is we're going to try to apply the rational root theorem to this problem right here. Now, rational means whole numbers, integers, or fractions. Irrational is when the square root symbol is involved. So if we have integer coefficients, what we're going to try to do is figure out how many possible rational roots are possible. Rational roots are things that also are factorable. That's important to us because if we're using factoring, it's important to know that what is possible as far as factoring goes. So to find what we call the rational roots, our first step is to find the factors of P. So P is the negative 6. So again, if I use a t-chart, what I'm picking up on is, I have a 1 and a 6, a 2 and a 3. So what we pick up on is the factors are going to be like a positive or negative 1, a positive or negative 2, a positive or negative 3, or a positive or negative 6, because we could alternate back and forth to get this negative 6. So when you list the factors of 6, list them as plus and minuses as well. So my next step is to find the factors of the Q, which is the leading coefficient. So the 2, really, there's only 2 factors of 2, 1 times 2. So what we have here is plus or minus 1 and plus or minus 2. So now to list the possible factors or the possible rational roots, what we do is we write P over Q. So let's just start with the 1. So I have plus or minus 1 over plus or minus 1. So this one goes with this one. And then I'm going to do the same thing with the plus or minus 1 is going to go with this one. So you're going to have plus or minus 1 over plus or minus 2. And let's make that easier. Let's not put all these plus or minuses in. Let's just put the plus or minus out in front. Make it a little bit less confusing. We don't need all those. We just need just one set of plus or minuses here. So let's just put the plus or minus out in front. Plus or minus 1 over 1 plus or minus 1 over 2. Let's just do it that way. Then I do the same thing with the 2. I put the plus or minus 2 over each one of these factors of q. So it's going to be plus or minus 2 over 1 and plus or minus 2 over 2. And then we're going to do plus or minus 3 over 1 and plus or minus 3 over 2. And then we're going to have plus or minus 6 over 1 and plus or minus 6 over 2. So now we want those lowest terms. So 1 over 1 really is the same thing as plus or minus 1. Plus or minus 1/2 is in lowest terms. Plus or minus 2 over 1 is really the same thing as plus or minus 2. 2 over 2 is really the same thing as plus or minus 1, so we've already used that one. Plus or minus 3 over 1 would be the same thing as plus or minus 3. Plus or minus 3 over 2 is different. Plus or minus 6 over 1 will be just plus or minus 6. And 6 over 2 is the same thing as plus or minus 3, so that is really just repeated. So that would be our list of possible factors for this polynomial function. So what do we do with this information? Let's see what we have going on next here. So if we want to find the real zeros of a polynomial function, let's see what else is going on here. So to start with, the degree indicates the maximum number of real zeros. So there are 3 possible. Now, it doesn't mean there has to be 3. There just can't be any more than 3. Descartes rule of signs helps us identify how many are positive and how many are negative. So if I evaluate f of x, I see that it's positive, positive, negative, negative. So I'm only seeing one sign change. So as far as possible positive, we're seeing one positive is possible. If I evaluate f of negative x, that's going to tell me how many negative real zeros are possible. So again, when I put the negative in, a negative raised to the 3rd power makes that negative. So that's a negative 2x cubed. A negative raised to the even power does not change the sign, so it stays as plus 11x squared. A negative and a negative make that a positive 7x, and the negative 6 comes along for the ride. So as far as the sign changes go here, it's negative, positive, positive, negative. So negative to positive is a change. That's positive still. Back to a negative is another change. So I'm seeing 2 sign changes. So there's either 2 or 0 negative real zeros possible. So we pick up on that information to start with. So the possible rational roots. So the rational zeros, if it's rational, that means it's a factorable problem. So we focus on the constant and the leading coefficient. So the factors of the constant, since the constant is a negative 6, notice how we really don't have to put the negative in there. So we pick up on the factors of 6 would be like, if I use my t-chart, the factors of 6 would be 1 and 6, 2 and 3, and that would be it. So we're going to use a plus or minus 1, a plus or minus 2, a plus or minus 3, a plus or minus 6. Those are my different factors of my constant. So the factors of my leading coefficient, well, my leading coefficient was that 2. So 2 is my leading coefficient. So again, the factors of 2, really, there's only 2 factors, 1 and 2. So again, I'm just going to have plus or minus 1, plus or minus 2. So the possible rational zeros, we just use P over Q. So I'll go 1 over 1 is, well, that's just plus or minus 1. 1 over 2 would be plus or minus 1/2. Then I move to the 2. Plus or minus 2 over plus or minus 1, or just 2 over 1 would be 2, plus or minus 2. 2 over 2 would be the same thing as plus or minus 1, which we already have. 3 over 1, plus or minus 3, plus or minus 3 over 2. And then we do plus or minus 6 over 1 would just be 6. And 6 over 2 would be 3, which we already have that. So now we want to test the possible rational zeros until one is found. So what we can do is we can evaluate f of p over q. So what I could do is I can do f of 1 to start with. So what I can do is, using my calculator, I can put that function in to help me out, expedite this a little bit. So my function was up there. So I have y equals 2x cubed minus, I don't have that one in there, do I? So let's clear that off. So I have 2x cubed plus 11x squared minus 7x minus 6. May want to double check that, make sure it's right, because you're going to be relying strictly on that at this point. I think we're okay. So when I go to the table now, I'm going to delete these off here. And so now I'm doing f of 1. And also I get 0. So right off the bat, I'm picking up on, I found one already. So f of 1 gave me 0. So until I found one, so I'm already done with that. So now what I can do is pick up on that x minus 1 is going to be a factor of this thing. So x minus 1 becomes a factor. Since 1 was a 0 or factor, it's going to be x minus 1. So what I can do now is I can use synthetic division, and I can divide this by x minus 1. So using synthetic division, I'm going to have this 1 comes out here, and make sure your exponents count down 3, 2, 1, 0. So I have a 2, 11, a 7, and a negative 6. So with synthetic division, we bring down the 2. The 11, 1 times 2 is 2. That gives me a 13. 1 times 13 is 13. And we're not getting this to work, are we? Do we miss something? So 1. So something's looking a little confusing here. It looks like what I may have done is this should have been wrote the problem down wrong. That should be a minus 7x there. So should have a minus 7x there, which is going to make this a little bit different here. So let's back up a little bit. And this should be a minus 7x that we're working out here. Okay, so when I do my synthetic division, I should have the coefficients of 2, 11, a negative 7, and a negative 6 here. So 2 comes down, 1 times 2 is 2, 13 comes down, 1 times 13 is 13, negative 7 plus 13 is a 6, 1 times 6 is 6, and negative 6 plus 6 is 0. So that now works out just fine. So my remaining polynomial is now 2x squared plus this 13x plus 6. It's equal to 0. So since we have a quadratic at this point, we should be able to find the remaining factors by using factoring. So let's see if we have some luck with factoring on this thing. So if it doesn't factor, then we have to do something else. But the factors of 2x squared, they're locked in. We have a 2x and an x. But the catch is there are several different factors of 6. So, we could use 1 and 6. So let's go 1 and 6. We'll put a 6 here and a 1 here. And we'll use the outer and inner terms to see if I get the middle term. So 2x times 1 is 2x. 6 times x is 6x. And that's going to give me this 8x. I need a 13x. So let's switch the places of the 6 and the 1 to start with and see what that does. So put the 1 here and put the 6 there. So that's going to now give me a 12x. And this is going to give me a 1x. So that's going to be 13x. So that does factor out. So we can now set each one of these factors equal to 0. So let's come down here. I got a little bit more room down here. So I have this 2x plus 1 times this x plus 6 becomes the factors of the quadratic. So I set each one of those equal to 0. So 2x plus 1 is equal to 0. X plus 6 is equal to 0. So I have x equals negative 1/2 and x equals negative 6. So I found those two zeros. So what we've picked up on then is the zeros are, we found 1, we found negative 1/2, and we found negative 6. So based on some of the stuff that we talked about, Descartes rule of signs, if we go up here at the top here, Descartes rule of signs says there's only one positive possible and 2 or 0 negative ones. So notice how we did get 1 positive and we did get 2 negative rational real zeros. So that kind of verifies it. And also we were supposed to only find no more than 3, and we found 3. So that all checks out. So that's our zeros. So 1, negative 1/2, and negative 6. So let's try see if we can walk through another one of these examples. So find the real zeros of 2x to the 4th minus x cubed minus 5x squared plus 2x plus 2. So the maximum number of real zeros, notice how the degree is 4. We know there's 4 possible. Using the Descartes rule of signs, the number of possible real zeros, we just count the sign changes in the original function. So it's positive, negative, that's a change. It stayed negative, went back to positive, that's a change. And stayed positive. So I see 2 or 0 would be that. So the maximum number of possible positive real zeros would be 2 or 0. To find the number of negative real zeros, we have to evaluate f of negative x. So if we put a negative x in for x in each spot, so we have a negative raised to the even power, that means no sign change. That says it's 2x to the 4th. A negative x to the 3rd power that stays negative, and there is a negative there, so it turns into a plus x to the 4th. Since there's 4 negatives, that makes it positive. Negative x squared, that's going to make that positive, so that stays a negative 5x squared. Oops, where did I go wrong here? Okay, I think I should add a 3 there. Plus x to the 3rd. Minus 5x squared stays put. Minus 2x plus 2. So now if we count the sign changes here, it's positive, stays positive. It goes to negative, there's a change. It stays negative, but then it flips back to positive, so there's another change. So that means there's going to be either 2 or 0 possible negative real zeros. So now I want to find the possible rational zeros. So what I need is the factors of p. So p comes from the constant. So that's 1 times 2 is it. So I'd have plus or minus 1 plus or minus 2. The factors of q, again, since it's just a 2, it's just going to be a 1 and a 2 again. So plus or minus 1, a plus or minus 2. And so the possible rational zeros is going to be p over q. So I put 1 over 1 would be plus or minus 1. 1 over 2 would be plus or minus 1/2. And then I put 2 over 1. That's going to be plus or minus 2. And 2 over 2 is the same thing as plus or minus 1. So those are my possible rational zeros. So we want to test those possible rational zeros. So in doing so, I'm going to type in 2x to the 4th minus x cubed minus 5x squared plus 2x plus 2 in my calculator. So I'll clear this off here. And I'm going to put in 2x to the 4th minus x cubed minus 5x squared plus 2x plus 2. So if I hit second table, I can delete that off and start again. So let's start with 1 again. Let's see what happens. Notice how 1 does work right off the bat. So we really don't have to do a whole lot of testing here. So we found that f of 1 is equal to 0. So that means that x minus r is a factor. X minus 1 is a factor. And 1 is a 0. So what I can do here is, since I found a rational 0, I can use synthetic division to pull that out. So I have 1 comes out. And I'm now going to have, so this 1, I have this 2, negative 1, just use the coefficients. So 4, 3, 2, 1, 0, nothing's missing. Negative 5, 2, and 2. So using synthetic division, I bring down the 2. 1 times 2 is 2. That gives me a 2. There's a positive 1. 1 times 1 is 1. That gives me a negative 4. 1 times negative 4 is negative 4. That gives me a negative 2. 1 times negative 2 is negative 2. And that gives me a remainder of 0. So my new polynomial is, since we had a degree 4, it's going to now be a degree 3. So it's going to be 2x cubed plus x squared minus 4x minus 2. And since this is a degree 3, we've done degree 3s by grouping. Let's see if this will actually factor by grouping. So if it doesn't, then we can continue on with our rational root theorems and things like that. Okay. So again, in factoring by grouping, I'm going to group the first 2 together, the second 2 together, and see what we can do here. So the GCF of the first 2 is an x squared. So pull out an x squared, and I'm left with then I'm left with, looks like a 2x plus 1. And remember, in this next position, since there's a negative in that front position, we pull a negative out. And they also have a 2 in common. So I'm going to pull out a 2. And that's going to give me then a 2x plus 1. So now what I have is, since there's a 2x plus 1 in common, I can pull that out. So I have 2x plus 1. And I have this x squared minus 2 left. So now I can set each one of those equal to 0. 2x plus 1 is equal to 0. And that's going to equal x equals negative 1/2. X squared minus 2 is equal to 0. I can isolate the negative. I can isolate the x squared on one side and go x squared equals 2. And I can take the square root of each side and I'd have x equals plus or minus the square root of 2. So I would have that as 2 roots as well. So we found 1 up there. So we did that. So we set each one of those factors equal to 0 here, and we solved already. So we ended up with x equals 1. We have this negative 1/2, and we have a square root of 2, and we have the negative square root of 2. So we found 4 zeros. 1 is positive, or sorry, 2 are positive and 2 are negative. And I think that's what we were talking about up here. You could have 2 positive or 2 negative. So we end up with those as our solutions. Keep in mind, you can also use your graphing tools and you could find the zeros as a way to verify the math. So if you're like really unsure of these, you actually could pick up and graph it as well. So if I hit y equals, and I already wrote the function in, if I hit the graphing button, you can kind of see we have that going on. If I hit the zoom button, if I use box number 1, I can get a really closer look at this at these x-intercepts or zeros. Went the wrong way there. Come back here. So if I go to the left a little bit, a little too much. Just get really up close. If I hit enter there, lock in my box, come down, go across there, get that other spot in, because that's where all my zeros are. Hit enter. I can get a closer look at my graph. Also, if you want, we can find, see if these are actually the zeros. So above trace is calculate. If I hit second calculate, number 2 is 0. So if I hit 2, I can come down here to each one of these zeros, see if I can find myself. There he is. I got to get left of my first 0. So I'll get to my left bound there, hit enter, get my lower bound or my right bound. That's to the right of it, hit enter again. Notice that I get this negative 1.14. I wonder if that's what that square root of 2 is. So if I hit second quit and do the square root of, which is above the x squared, second square root of 2, hit enter. Notice that does give me this 1.14. So yeah, that's going to be that square root of 2. So I'm kind of seeing that we're seeing those x-intercepts appear in my graph. So if I hit the trace button and just let it follow along instead, you know, see what it gets when it gets over here. So is that actually, notice how negative 0.5 is really, really close to negative 1/2. So that looks good. Come on back down. There he comes. So notice that that's really close to 1. So I'm really feeling good about that one. And my third 0, again, that's right at that negative 1 or sorry, 1.42. I think that's what we said. If I quit out of that, you know, it's 1.4 as well. So yeah, we've got the zeros there to do that. All righty. So that concludes my lesson for 5.6, I believe it was, solving rational or polynomial equations for their zeros. Okay, let me see, go back over the top real quick here and yeah, finding the real zeros. So real zeros mean you can have rational and irrational. That's why we had that square root 2 and negative square root 2 there. All right, see where that takes you. Have a good day.